The Atomic Bomb by Saúl de la Fuente, Javier Mejía, Martin Perez, Ángel Martínez, and Christian Hipólito. Table of content: biography, how it works, difficulties faced, what it can do, effects on physics.
Early life. Robert Oppenheimer, born into privilege in April 2nd, 1904, in New York City, displayed remarkable intelligence and a thirst for knowledge from a young age. Growing up in an affluent environment, he attended the Ethical Culture School in Manhattan, where his academic prowess and passion for science flourished. At Harvard University, Oppenheimer found his calling in physics under the mentorship of Peter Bridgman, graduating summa cum laude in just 3 years. His journey continued in Europe, where he studied under renowned physicists at the University of Cambridge and the University of Göttingen, culminating in his completion of his PhD in 1927. At the age of 23, these early experiences laid the groundwork for Oppenheimer's future contributions to theoretical physics and his pivotal role in the development of the atomic bomb. During the Manhattan Project, J. Robert Oppenheimer served as the scientific director, leading a team of scientists at Los Alamos, New Mexico, in the development of the atomic bomb. His leadership and expertise were pivotal in coordinating the efforts of physicists, engineers, and other specialists involved in the project, culminating in the successful detonation of the first atomic bomb at the Trinity test site on July 16, 1945. However, Oppenheimer grappled with the ethical implications of creating such a devastating weapon, leading to a personal struggle and self-doubt. Despite his contributions to the project, Oppenheimer's involvement in the development of the atomic weapons thrust him into the spotlight as a prominent figure in American science and politics, shaping his view on science, society, and humanity. The McCarthy Trials. During the McCarthy Trials, J. Robert Oppenheimer faced intense scrutiny and controversy due to his past associations with leftist groups and his opposition to the development of the hydrogen bomb. His involvement in left-leaning organizations and his vocal dissent against certain government policies led to suspicions of his loyalty to the United States government. Despite his significant contributions to the Manhattan Project and his reputation as a brilliant physicist, Oppenheimer's past political activities made him a target during this era of heightened anti-communist sentiment. The hearings cast a shadow over his legacy, and his security clearance was ultimately revoked in 1954, effectively ending his official involvement in government science projects. After the McCarthy trials and the loss of his security clearance, J. Robert Oppenheimer experienced a notable shift in his career trajectory. Despite the setback, he maintained his dedication to academia and scientific inquiry, returning to teaching and focusing on theoretical physics. Oppenheimer held esteemed positions at institutions such as the Institute for Advanced Study in Princeton and the University of California, Berkeley. While his involvement in government science projects waned, his influence within the scientific community endured. Oppenheimer's post-McCarthy era marked a period of reflection on the intersection of politics, science, and ethics, leaving a lasting imprint on both the scientific landscape and broader societal discourse. In his later years, J. Robert Oppenheimer, despite the controversy surrounding his security clearance revocation, remained a prominent figure in academia and theoretical physics. Transitioning away from government projects, he focused on teaching and research, holding prestigious positions at the Institute for Advanced Study in Princeton and the University of California, Berkeley. As director of the Institute from 1947 to 1966, Oppenheimer mentored young physicists and pursued his own research in quantum mechanics and astrophysics. At Berkeley, he continued to contribute to academic discourse and research, maintaining his intellectual vigor and influence within the scientific community. Despite the challenges he's faced, Oppenheimer's passion for physics and dedication for advanced scientific knowledge left a lasting legacy, inspiring future generations of scientists and scholars. Oppenheimer passed away on February 18, 1967, leaving behind a profound impact on physics and academia.
Hello, my name is Christian Ippolito, and for this part of the presentation, I will be discussing the science behind the atomic bomb. An important feature of the atomic bomb is the process of nuclear fission. Nuclear fission is when the nucleus of an atom splits into multiple and emits a large amount of energy. In this process, neutrons are emitted from the atom, and those neutrons then hit other atoms and continue a chain-like reaction. This is a central process that produces the explosion of the atomic bomb. To effectively complete the fission process, it is important to use materials that are capable of sustaining fission. In the Hello, my name is Christian Ippolito, and for this part of the presentation, I will be discussing the science behind the atomic bomb. An important feature of the atomic bomb is the process of nuclear fission. Nuclear fission is when the nucleus of an atom splits into multiple and emits a large amount of energy. In this process, neutrons are emitted from the atom, and those neutrons then hit other atoms and continue a chain-like reaction. This is a central process that produces the explosion of the atomic bomb. To effectively complete the fission process, it is important to use materials that are capable of sustaining fission. In the Manhattan Project, uranium and plutonium were the two main elements used to serve as the fissile material. Compared to other elements, the atoms of uranium and plutonium have a high chance of splitting. It is important to have multiple variations. Some of these variations are stronger for fission, while others are weaker. For instance, most of the uranium naturally found, called uranium-238, is weak for fission. On the other hand, uranium-235 is much more rare but a very effective material for fission. While uranium must be found naturally, plutonium can be chemically produced through beta decay. Beta decay is a form of radiation and disintegration. Hello, my name is Christian Ippolito, and for this part of the presentation, I will be discussing the science behind the atomic bomb. An important feature of the atomic bomb is the process of nuclear fission. Nuclear fission is when the nucleus of an atom splits into multiple and emits a large amount of energy. In this process, neutrons are emitted from the atom, and those neutrons then hit other atoms and continue a chain-like reaction. This is a central process that produces the explosion of the atomic bomb. To effectively complete the fission process, it is important to use materials that are capable of sustaining fission. In the Manhattan Project, uranium and plutonium were the two main elements used to serve as the fissile material. Compared to other elements, the atoms of uranium and plutonium have a high chance of splitting. It is important to have multiple variations. Some of these variations are stronger for fission, while others are weaker. For instance, most of the uranium naturally found, called uranium-238, is weak for fission. On the other hand, uranium-235 is much more rare but a very effective material for fission. While uranium must be found naturally, plutonium can be chemically produced through beta decay. Beta decay is a form of radiation and disintegration. A major obstacle the scientists of the Manhattan Project faced was creating an atomic bomb with self-sustaining chain reaction. To achieve this, the atomic bomb was created to achieve a critical mass. Critical mass is when the right amount of uranium or plutonium is used in the bomb for the chain reaction to self-sustain itself. Once the critical mass is achieved, the atomic bomb is able to release massive amounts of energy and explode. Hello, my name is Christian Ippolito, and for this part of the presentation, I will be discussing the science behind the atomic bomb. An important feature of the atomic bomb is the process of nuclear fission. Nuclear fission is when the nucleus of an atom splits into multiple and emits a large amount of energy. In this process, neutrons are emitted from the atom, and those neutrons then hit other atoms and continue a chain-like reaction. This is a central process that produces the explosion of the atomic bomb. To effectively complete the fission process, it is important to use materials that are capable of sustaining fission. In the Manhattan Project, uranium and plutonium were the two main elements used to serve as the fissile material. Compared to other elements, the atoms of uranium and plutonium have a high chance of splitting. It is important to have multiple variations. Some of these variations are stronger for fission, while others are weaker. For instance, most of the uranium naturally found, called uranium-238, is weak for fission. On the other hand, uranium-235 is much more rare but a very effective material for fission. While uranium must be found naturally, plutonium can be chemically produced through beta decay. Beta decay is a form of radiation and disintegration. A major obstacle the scientists of the Manhattan Project faced was creating an atomic bomb with self-sustaining chain reaction. To achieve this, the atomic bomb was created to achieve a critical mass. Critical mass is when the right amount of uranium or plutonium is used in the bomb for the chain reaction to self-sustain itself. Once the critical mass is achieved, the atomic bomb is able to release massive amounts of energy and explode. The atomic bomb pan, also known as Fat Man, was built with an implosion design. In this design, the Fat Man is shaped in a sphere of two layers, a core and a shell around the core. The core was made up of plutonium, while the shell surrounded this core full of traditional explosives. Once the bomb was ready to explode, the explosives would detonate and compress the plutonium core until critical mass was reached and the fission process began. This design allowed for both plutonium or uranium to serve as a fissile material to carry out the fission process. Nonetheless, plutonium was used in the Fat Man as the core. This kind of test.
Difficulties faced. The scientific concepts behind the development of the atomic bomb predate World War II, but it was World War II that really kick-started the development of the bomb during the Manhattan Project. As expected, developing a novel weapon of mass destruction while also fighting a war on multiple fronts brought with it many challenges to the scientists and experts involved. The task of developing the bomb itself was demanding in terms of both labor and expertise. Scientists with expertise in various backgrounds such as material science, nuclear physics, and chemistry were integral to the project. In addition to the areas of expertise needed to develop the bomb, scientists were facing immense pressure by the government as there was a strain on financial resources and the threat of the project being compromised via espionage attempts. Lastly, one of the biggest issues that scientists had with the bomb was the ethical implications of making a weapon capable of such destruction. These ethical concerns would soon prove to be justified, seeing as how nuclear proliferation is more relevant in today's affairs than ever. Materials. The Manhattan Project required a multitude of various resources in order for the making of the bomb to be successful. However, the two most significant resources required for the making of the atomic bomb were uranium-235 and plutonium-239. These isotopes were needed in much larger quantities than their natural elements could provide. So to compensate, large reactors along with the supporting infrastructure were built with the purpose of harvesting the desired isotopes from their elements. This, however, was no modest feat. In addition to dealing with radioactive isotopes, scientists also needed large and expensive infrastructure for the reactors responsible for harvesting the isotopes from their elements. The transportation of these materials was also a major challenge. The facilities at Los Alamos and other sites required vast amounts of construction materials such as steel, concrete, and lumber, which were especially high in demand because of the war. In addition to raw materials, the deployment of the bombs also required sophisticated electronic components, which at the time were difficult to produce in very large quantities. Scientific expertise. The development of the atomic bomb utilized many concepts and ideas in physics, but involved many other areas and fields of study. This meant that they needed assistance from scientists with backgrounds in also chemistry, engineering, and also material science. In addition to the need for many experts in various fields of study, finding these experts and scientists was also another difficult task, since some of the scientists were from countries part of the Axis. One of the most notable scientists that partook in the making of the atomic bomb, and who was also from one of the countries part of the Axis, was Albert Einstein. Experts from all of these fields needed to find a way to combine their skills and knowledge to collaborate with each other in order to make a task as complicated as building an atomic bomb successful. Lastly, one of the primary concepts that scientists needed to understand well was nuclear fission. This was the main driving force behind the atomic bomb and was where most of the project directed its resources to. All of these various fields in some way were expanded upon and improved upon because of the Manhattan Project and are still relevant today. Espionage attempts. While the development of the atomic bomb brought with it plenty of challenges to overcome on its own, the ongoing war at the time also brought its own issues. Since countries were at odds with each other, there was a desire from each superpower to find or discover new weaponry that could aid in the destruction of their enemy. This meant that maintaining the secrecy of the Manhattan Project was also a major concern for the US government. This put a restraint on international collaboration and the sharing of knowledge, both things which are integral to the foundation of science itself. Despite the US government's efforts at preventing espionage, opposing and even allied countries were still unfazed and still actively trying to sabotage the project. These espionage attempts also meant that the transportation of the materials was made much more difficult. These attempts at espionage were a major hurdle for the United States to overcome during World War II, but they also played a role in the fueling of the Cold War. Once again, we see that the Manhattan Project indirectly influenced other events in history that would soon come. Ethical dilemmas. Though there were many breakthroughs and ideas in physics that came with the bomb, many of the experts involved had ethical concerns with the creation of such a powerful weapon. Scientists were primarily concerned with the fact that if the development of this bomb was successful, who should control these weapons? One of the most notable examples of this was a petition called the Frank Report. This was a report drafted by a group of scientists from the Manhattan Project, which suggested to the US government that the bomb should be tested on an uninhabited area rather than a populated area. Oppenheimer had also expressed his discontent with the bomb by famously quoting, "Now I am become death, the destroyer of worlds," which is derived from text from the Bhagavad Gita, a book from Hindu scripture. Needless to say, most of the scientists at the time, including Oppenheimer, expressed the same sentiment towards the bomb, and their concerns at the time proved to still be relevant in today's affairs.
So, what the atomic bomb can do. Generally, it's depicted as something very violent and gruesome, and that is correct. I have listed that usually it's known for its mass destruction, the death it can cause, the injuries, and something kind of more overlooked is the radiation. There are many effects of what an atomic bomb can do, mainly being violent and detrimental to its environment, as it can demolish cities or towns within seconds. It's a lot that happens, and the blast radius is super huge. The radiation, everything just adds on to it and makes it very gruesome. And hopefully we don't see more uses of it. So, on the topic of its mass destruction, generally, it's used for that, and the destruction of a city/town is one of the most known uses and reasons for its existence. The radius of the explosion is highly reliant based on weather conditions, but it can also have a radius of 1 mile to put into perspective, which can be translated into roughly 1,609 meters. The force of the atomic bomb explosion can have 21,000 tons. When you have both of them added up together with the radius and the force, you can put into perspective how impactful it is. With an enormous blast radius along with a powerful force, it's quick to see why they were used, because of its effect. So, along with its blast, there's another level to it, an aftermath, and that's the radiation. Now, along with its direct source of ability, it leaves an after effect being negative to the environment around it. After the detonation, particles fly into the air. These can be big or small ones. Usually the bigger ones just fall to ground zero. But the smaller ones, particles fly into the air as far as 50 miles and join the upper atmosphere. The wind can carry them over, and it can easily spread. And the lighter particles that I just mentioned that do join the air and atmosphere are then known as fallout. So they have a term for it. And they're very small particles. They have a name known as nuclides. And, you can imagine the effect it can have on the person. And they go very far, and we're going to talk about the effects right now. So, quickly explaining what nuclides are. In general, nuclides are atoms or nucleus with a set number of protons or neutrons. Now, actually, I mentioned nuclides earlier. I meant to say radionuclides. That's my fault. But within the fallout, radionuclides can be found. These are basically similar to nuclides, but with an exaggerated amount of protons or neutrons, which leads them to be more unstable. Now, radionuclides can be seen from a fallout, and the lifetime of these can stay alive for a number of years, even 30 years, or they can easily die within seconds. Why does this matter? We can consume these radionuclides because of the spread from the original detonation. Once we are contaminated, a large number of negative effects impact our lives. Following along with the effects of radionuclides. So the consumption of radionuclides can lead to a number of serious diseases, many negative effects. So the consumption of it can lead to skin damage, cataracts, and potentially even death if it's super serious. The inhalation of radionuclides can also lead to diseases such as chronic lung disease. So these are very small things that can go unnoticed, and that's why it's super important to take care of these test and let the people know what's going on, and we do have such systems involving the surveillance of it to keep people at bay. And along with these two main impacts of what the atomic bomb can do, along with it are more things that are overlooked, such as the use of the production of heat, light, and even an EMP. So of course, if you're closer to it, you're gonna, if you're looking at it, you're gonna cause blindness. If you see in movies, flashes of white light come out, and it's important not to look at it unless you have goggles. And burns, of course, if you're super close to it, of course. And it will release an EMP effect and damage unprotected electronic equipment. This is kind of more of a subtle thing, and this was found out through the testing of atomic bombs.
The atomic bomb's effect on physics. In order to create the atomic bomb, scientists needed a comprehensive understanding of fission, and with that comes a detailed understanding of atoms, as it is atoms that are used in fission. They also needed to know how to make and test specific elements in order to maximize the effectiveness of the atomic bomb. How to create fission within a bomb, as it had previously only been done inside of large laboratories, and we would need them to be inside of relatively smaller bombs. We also needed to know how and when to detonate the atomic bomb, as we had previously only had rockets and missiles which explode upon impact, and the atomic bomb would not work if it is not detonated before impact. Fission occurs when the nucleus of an atom is bombarded with neutrons. This causes a separation in the nucleus, forming lighter elements. Fission was first discovered by Lise Meitner and Otto French in 1938. Scientists later discovered that if enough neutrons bombarded the nucleus, it would create an enormous amount of energy. Scientists needed to understand how neutrons split the nucleus and created such a large reaction. Scientists also needed to understand which elements would produce a more desirable reaction for creating the atomic bomb. When testing which elements produced the most desirable outcome, scientists found that uranium and plutonium created an explosion equivalent to 15,000 tons of TNT, devastating 11.4 square kilometers. However, uranium-235 and plutonium-239 were not abundantly available in nature, so scientists had to create factories in order to create these elements for further testing and later use in the atomic bomb. Scientists were faced with the challenge of putting fission inside a bomb. Fission had only previously been tested in large laboratories, so fitting everything needed to precisely launch neutrons at an atom's nucleus inside of a payload that could be delivered by a plane in the 1940s would prove to be difficult. Scientists also needed to create a remote detonation for the atomic bomb, since we had previously only used rockets and missiles that explode upon impact. The fission would need to be initiated before the impact to maximize its effectiveness. In order to be able to create and use the atomic bomb, scientists needed extensive knowledge of fission to be able to use it inside of a vessel that could be carried by a plane. This furthered our understanding of elements by having us study the elements to understand how they act, how they react, which ones react more, which ones don't react as much. And by being able to remotely and precisely launch a neutron at an atom's nucleus inside of a confined space while it is being dropped. Here are our first 5 references. These are our last 5 references. Thank you.